Hi everybody, Joy here, and in today's video we are moving from graphs to data, which is the opposite direction compared to what we've been doing previously, which is using data to construct graphs. But now we're going to interpret graphs and take the graph, see if we can pull it apart a little bit and understand the data that underlies it. So here we have an example of a histogram, and we want to understand a little bit more about the data. And to be able to do this, I always suggest that we start with three kind of categories or questions that we're dealing with. The first is, what is the data shaped like? What does it look like? And then I want to find out both the dispersion and the central tendency of my data. So dispersion, as you know, is just a fancy word for how spread out the data is. And central tendency, those measures are ways to describe what a quote-unquote typical data point would do. What does data tend to do? And we know that there's several different measures for dispersion as well as for central tendency. But first, let's talk about the shape. So the first thing that I see when I look at this graph, and the first question I generally ask is, does this graph show any evidence of symmetry? And this graph clearly does not show symmetry. Let me make a circle so you can see where my mouse is. So we've got a tall cluster, sort of a shorter cluster, and then we've got a few little data points out here. But there's no evidence of any kind of symmetry. This is an asymmetric distribution. And it's got how many peaks? How many sort of local hills are there? And we see that there's one sort of pile of data over here, and it's got a peak here. This bar is definitely the tallest. And we have this middle guy here, and this is not anywhere near as tall as my first peak here, but it's pretty tall compared to its neighbors. So I'm going to say I have two peaks. I'm going to say that none of these guys are really peaks. They're more like data speed bumps, right? They're too low to be called a peak. So we've got two peaks here, and this is a little bit open to interpretation, right? This is qualitative, determining what you consider a peak. But I'm going to say we have two peaks, and because we have two peaks, I'm going to describe this as a bimodal distribution. And if I had one peak, I would say unimodal. And if I had three or more, I would say it's multimodal. We just say multimodal if it's three or more. But this is an asymmetric bimodal distribution. And while we're looking at the overall shape of the data, I think it also makes sense to ask ourselves if this distribution looks familiar to us. Is it one of the distributions that we've seen before that has a special name? For example, is it bell-shaped, which is a normal distribution, or you might hear people say a Gaussian distribution? Well, that's not the best one, but pretend that's perfectly symmetrical. Well, nope, that's definitely not a normal distribution. And I could also ask the question if it is uniformly distributed. And uniform, again, you can have a few little deviations here and there. It doesn't have to be perfect. But is it more or less uniformly distributed? And the answer to that is also no. So I'm not going to add any extra word here about its a special kind of distribution whose name I know. I'm just going to leave it be by saying it's asymmetric and bimodal. Now let's talk about dispersion for just a bit, how spread out our data is. We know that there's a few ways to measure dispersion. We have talked about the interquartile range, and we have talked about standard deviation. I'm just going to abbreviate that. But both of those are going to be really hard to discern from this kind of data. The IQR especially is really easy to discern in a box plot, but not so much in a histogram. It's very hard to determine. But what we can tell is the overall range, not the interquartile range, but the range from highest to lowest here. And that looks like it's between 0 and 10, maybe around 5, I'm going to say, and 65. So I can say my range, kind of run out of room here. My range is is 5 to 65. And that gives me a little bit of an idea of the dispersion. And I saved central tendency for last because in some ways it's the most important and also the most difficult to do in a histogram, especially one that is not symmetric. If you have a symmetric graph, especially if it's normal, that's really easy. Again, pretend it's symmetrical. It's easy to tell where the mean is. It's right smack dab in the middle, but we don't have a graph like that. So the question is, what can I figure out? Let me just change ink colors again. What can I figure out? Well, we've got three measures of central tendency that we've talked about. We've talked about the mean and the median and the mode. So let's start at the last one because that's going to be the easiest in any histogram. If the mode is the most frequently occurring data point and the histogram is a frequency graph, what you want to do is look for the highest point. So what is the highest point on this graph? It's right around here, right? So I'm just going to go down here and say my mode looks like it's maybe about 7, right? Roughly. It's roughly 7. And interestingly, remember how we said before that our shape was bimodal? So even when we're talking about the shape, the overall shape of the data, we're talking about frequency. And that's really easy in a histogram. So when we describe the shape and we've identified some peaks, we're already really close to figuring out the mode. The big difference here is that we don't want to do local peaks like this guy here. He doesn't count as a mode as far as our central tendency is concerned. We want really the highest peak. And there could be a tie, right, if there was another frequency out here that was equally tall. But we're not going to go down to our sort of local peaks. We want the overall tallest data point that we have. So that's mode. But what about mean and median? These are a little bit tricky. And for these, I'm going to ask you to put on some memories from early childhood and the playground. So if you had in your school or the playground close to your house, you had a seesaw, then you know a lot about how to find the mean, because finding the mean in a histogram is as simple as finding the center of mass. So imagine, if you will, that you're on a seesaw, or that these weights, if you can imagine these stacks as weights, are on a seesaw, and you want to balance out the weights using a pivot point. So if you put a pivot point out here on your seesaw, obviously that's not going to be balanced because this end is going to go down and this end is going to go up. So we're not going to put the pivot point there. Instead, we want to sort of move it back maybe to around between 10 and 20 at some point. And it's important to remember, too, when you're thinking about a center of mass, is if you can imagine, let's say you're a little kid. Well, let's say your friend is taller and bigger than you, and the two of you want to play on the seesaw. If you're a little kid, that won't work, right? But what you can do, and you figured this out probably when you were pretty young, you got the physics of it, is that if you moved backwards, you had a little bit more leverage. And even though you were smaller, the fact that you moved back on the seesaw meant that you would be in balance. And that's something important to keep in mind with our data here as well. So I've tried to put the pivot point, keeping in mind that I've got a couple points out here that, although they're not really big, they're going to exert a lot of influence to keep this end going down. So I think that the center of mass, or the balance point, is somewhere between 10 and 20. And again, this is a little bit open for interpretation. It's kind of tricky to tell on a histogram exactly where it is, but it's somewhere in that general ballpark. So we'll say the mean is around, I don't know, let's say 15. And that just leaves us with our median, and that'll be our next video.